In this video we present our paper, titled, Sim-to-Real Transfer of Visual Grounding for Human-Aided Ambiguity Resolution. In this work, we present a novel deep learning framework for language-guided visual reasoning of object attributes and spatial relations, aimed at solving the task of referring expression comprehension, in the context of human-robot interaction applications. Unlike previous works, that attempt to ground expressions in an end-to-end fashion, the key idea behind our approach is that, by decoupling visual representation from natural language understanding, we are able to train our model in simulation, and transfer it to natural scenes in a data-efficient manner, while entertaining high interpretability. We focus in an interactive grasping scenario, where a non-expert human user instructs the robot to pick an object from a crowded scene, using either an attribute or a relation to another object in order to disambiguate it from similar appearing items. We collect a selection of 60 household 3D objects, and generate a large-scale synthetic dataset of tabletop scenes, in order to train our model. The following examples demonstrate how our architecture accomplishes grounding of referring expressions with arbitrary complexity, using independent modules. A recurrent neural network module labels each word in the input query according to its semantic role, including entity, attribute, relation and location. Each role is assigned a specific module, which grounds the word in the set of objects detected in the RGB frame, using a feed-forward neural network that projects the object's visual features and the word embedding in the same space, and estimates their similarity. The frame in the right showcases the high similarity outputs of the entity module for the words, cereal box. Similarly, for the word, mug. An independent attribute module grounds the word, blue. Entity and attribute scores are aggregated with element-wise multiplication, to ground the object noun phrase of the input query, blue mug. A third module, responsible for grounding words describing spatial relations, produces a pairwise score for each object pair, and the relation word, behind. The visualization here displays all outputs that have high scores for being behind another object. Scores for grounding all three semantic roles in the phrase, subject, object and relation, are summed, and the item with the highest score is given as target goal for grasping. In this example, we show how the model deals with absolute relations, i.e. locations. A location word, like, rightmost, appears grammatically as an attribute, but implies a relation between a noun, and all other nouns of the same category, such that, rightmost Pringles, is equivalent to, Pringles, that is most right, from other Pringles. The use of phrase indices, together with the semantic roles in the word labels, enables our method to be extended to arbitrarily complex expressions that entail multi-hop reasoning steps. In this example, the model first resolves the secondary phrase, soda can behind flashlight, and uses the output as the object for the primary phrase, mug left from soda can behind flashlight. After training our model in simulation, we evaluated in natural scenes from two RGBD datasets, the Washington Scenes Dataset version 1, and a custom dataset, comprised of a subset of the objects used in simulation, however including novel attribute combinations. The decoupled nature of our model allows us to battle the domain gap between sim and real, solely in the visual domain. Instead of having to collect referring expression annotations for the real datasets, we use only a few images to adapt the visual representations, and transfer the rest of the architecture directly from sim, without any further training. We employ a popular semi-supervised domain adaptation technique, called domain invariant representation learning for sim-to-real transfer, as a pre-training step for our visual encoder, using our synthetic data, and up to 20 labeled images per object instance from the real datasets. In the TSNE figures, we demonstrate the incremental progression of the learned representations towards sim-to-real invariance, during this pre-training step. We integrate our method with a real robot framework, and showcase how it can be utilized for an interactive grasping scenario. During this round of experiments, we randomly place objects from our custom dataset in the table, and instruct the robot to pick an ambiguous object. In the examples that follow, we show the behavior of the real robot for different types of referring expressions. We highlight that our method is relatively robust to unconstrained queries that do not necessarily respect the training vocabulary, as well as novel attribute-object combinations. Additionally, the modular structure of our method allows us to diagnose the source of error in case of failures. Most failure cases are due to referring to unknown spatial relations, or grounding errors due to partial views of objects, leading to occlusion. Thank you for watching.